Welcome to this short but complete introduction to Python virtual environments. When I first heard about venv and pip, they sounded like extra complexity that I could simply avoid. Then I followed a Django tutorial that required both. I created a virtual environment, installed Django, and continued working through the tutorial over several days. I repeatedly forgot to reactivate the virtual environment, and whenever something stopped working as expected, my frustration with venv grew. The idea finally clicked when I started my first personal Django project. Python told me that Django was not installed, even though I had used it earlier that same day. That was when it clicked for me. Django was installed inside the tutorial project's isolated environment, not across my entire computer. A newer version of Django had just been released, so I created a separate environment for my new project and installed the latest packages there. The new project could move forward without breaking the tutorial project that depended on older versions. In this video, I'm going to save you the trouble of learning that lesson the hard way. Virtual environments are important, but they are not nearly as intimidating as they first appear. The entire workflow comes down to a handful of simple commands that are easy to remember, or easy to look up when you forget. Python's venv creates an isolated Python environment for a project. To understand why that matters, imagine that you have two Python projects on your computer. The first project depends on one version of a package, while the second project needs a newer version of that same package. If you install every package into your computer's main Python installation, all of your projects are forced to share those packages. Upgrading a package for one project could break another project that still depends on the older version. Over time, you may also forget which packages each project actually requires. A virtual environment solves this problem by giving each project its own place for Python packages and command line tools. Packages installed inside one virtual environment do not interfere with packages installed for another project. Despite the name, a virtual environment is not a virtual machine. It does not create another operating system, and it does not consume anything close to the resources required by a virtual machine. It is simply a directory containing a project-specific Python environment. Python includes the venv module for creating these environments, so we do not need to install a separate tool. The virtual environment directory is normally stored inside the project directory, but we do not add it to Git. Instead, we record the project's dependencies in a small text file. Anyone who downloads the project can then create their own virtual environment and install the required packages into it. The basic workflow is simple. Create the environment once, activate it whenever you work on the project, install the project's packages inside it, and deactivate it when you're finished. Now let's create a project directory and build our first virtual environment inside it. Now we'll create a small demonstration project and give it its own virtual environment. The mkdir command creates a new directory named venv.demo, and cd moves us into it. This directory will be the root of our project. This is where our project will live. If you're using Git as a versioning system, you would typically run git init here. But after we create our venv environment, we won't commit that folder to Git. We'll use git ignore to avoid that. For now, we'll create the virtual environment. Let's break that command down. Python 3 runs the Python 3 interpreter. The -m option tells Python to run an installed module. The first venv is the name of Python's virtual environment module. The second venv is the name of the directory we are asking it to create. That final name is our choice. In this tutorial, I'm using the plain name venv, so the directory remains visible during normal file listings. Some folks use .venv, but that makes the directory hidden, so we aren't doing that here. The command may take a few seconds to finish. When the prompt returns, we can list the project directory again. We now have a new directory named venv. Python created the virtual environment inside that directory. It contains a Python interpreter, activation scripts, pip, and directories, where this project's packages will be installed. At this point, the environment exists, but we have not activated it yet. Our next step is to inspect what Python created, and then activate the environment for this terminal session. Before activating the environment, let's take a quick look at what Python created. The exact contents can vary slightly among operating systems and Python versions, but on Linux we normally see a bin directory, an include directory, a lib directory, and a file named pyvenv.cfg. The bin directory contains the environment's Python interpreter, pip, and the scripts used to activate the environment. Let's look inside it. Here we can see commands named Python and pip along with several activation scripts for different command shells. The include directory is available for header files used by some Python packages. The lib directory contains the environment's Python libraries. Packages that we install with pip will ultimately be placed beneath this directory in a directory named site packages. Finally, pyvenv.cfg is a small configuration file containing information about this virtual environment and the Python installation used to create it. You normally will not edit any of these files by hand. Python and pip manage this directory for us. Now that we know what the environment contains, let's activate it. Now we'll activate the virtual environment. The source command reads and executes the activation script inside our current shell. After activation, the terminal prompt normally begins with the environment's name in parentheses. In our case, it displays venv, which matches the folder that we created earlier. That change in the prompt is a useful reminder, but it is not what makes the virtual environment work. The important change happens to an environment variable named path. Path contains an ordered list of directories that the shell searches whenever we enter a command. The activation script places venbin at the beginning of that list. This means the shell finds the virtual environment's Python and pip commands before it finds the system versions. Let's verify that. The displayed path now ends with venv bin python, showing that the Python command belongs to this project's virtual environment. We can check pip in the same way. Its path also points inside venv.bin. Activation does not start a virtual machine, launch a background service, or copy our project. It simply adjusts the current shell's environment so that Python-related commands use this project's isolated tools and packages. The activation applies only to this terminal session. A different terminal window will not automatically use this environment. Now that the environment is active, we can prove which Python interpreter is running and then install our first package. We can ask Python itself which interpreter is running. The path points to venv.bin python inside our project. This confirms that the active terminal is using the virtual environment's Python interpreter. Now we'll install two related Python packages. Request was commonly used to retrieve content from the web, while Beautiful Soup is used to parse and navigate HTML. Because our virtual environment is active, these packages will be installed inside this project's venv directory. I'm using python-mpip. So pip runs through the Python interpreter we have already confirmed belongs to our virtual environment. Pip downloads both packages along with any additional packages they require. We can test the installation by importing them and displaying their versions. Both imports succeeded, and Python displayed their installed versions. Notice that the package is installed using the name Beautiful Soup 4, but imported into Python using the shorter name bs4. Let's also see everything currently installed in the environment. The list contains requests in Beautiful Soup, along with the supporting dependencies that pip installed for them. These packages exist only inside this virtual environment. Our other Python projects remain unaffected. A virtual environment should not be stored in Git. It can be recreated, and it may contain thousands of generated files. We'll create a .git ignore file and tell Git to ignore the entire venv directory. The trailing slash identifies venv as a directory. We initialized Git earlier. Now we'll run git status on the repository and check its status. Git shows git ignore as an untracked file, but the venv directory does not appear. The environment is now safely excluded from the repository. We are not committing the virtual environment itself, so we need a small file that records the packages required by the project. Pip can generate that file from the active environment. Pip freeze produces a list of the installed packages and their exact versions. The greater than symbol redirects that list into a file named requirements.txt at the root of our project. Let's examine it. The file includes requests, Beautiful Soup, and the additional packages they depend upon. Unlike the venv directory, requirements.txt should be committed to Git. It gives other developers, and our future selves, a reproducible list of the packages used by this project. If we install, upgrade, or remove packages later, we can update the file by running the same command again. The greater than symbol replaces the previous contents with a fresh list from the current environment. Now Git can preserve the project's dependency information without storing the entire virtual environment. When we finish working on the project, we can deactivate its virtual environment with one command. The venv label disappears from the prompt and the shell restores its previous path. Let's check Python again. The command once again points to the system's Python interpreter. Deactivating does not delete the environment or remove its packages. It simply stops this terminal session from using them. Closing the terminal would have the same practical effect. Let's simulate leaving the project and returning to it during a later terminal session. First, we'll move out of the project directory. When we return later, we begin by moving back into the project. The virtual environment is still here along with its installed packages, but a new terminal session does not activate it automatically. We reactivate the environment using the same command as before. The venv label reappears in the prompt, and this terminal is once again using the project's Python interpreter and installed packages. Now let's add 3 empty Python files to represent the project's source code. The touch command creates the files if they do not already exist. Let's view the project directory. Our project now contains 3 Python source files, the requirements.txt dependency list, and the local venv directory. The source files and requirements.txt can be shared through Git. The virtual environment remains excluded because another developer should create a new environment on their own computer. In the next step, we'll use these files to simulate receiving the project in another directory and recreating its working Python environment. Finally, let's simulate another developer receiving this project without its virtual environment. First, we'll deactivate the current environment and return to the parent directory. We'll create another directory and copy only the project files that would normally be stored in Git. There's no venv directory here. The other developer creates a new one locally. Copying the source files, requirements.txt and .gitignore recreates the kind of project another developer might receive from GitHub, GitLab, or another code repository. The virtual environment itself is not included in the repository. Instead, the developer creates a new one in the project's root directory by running Python 3-mvenv, exactly as we did earlier. They can then install every recorded dependency from requirements.txt. Pip reads the file and installs the recorded package versions into the new virtual environment. Let's confirm that our 2 packages are available. The imports succeed. We copied the project's source code and dependency list, then recreated its working Python environment without copying or committing the original venv directory. Let's recap what we've learned. Python's venv module solves the problem of package and version conflicts between projects. Each project receives its own isolated Python environment, so installing or upgrading a package for one project does not interfere with another. We create an environment with Python VENV. We activate it with source activate. Activation places the environment's bin directory at the beginning of path. This causes the terminal to use the environment's Python and pip commands. While the environment is active, pip installs packages inside that project's venv directory. The venv directory is generated and should not be committed to Git, so we add venv to gitignore. Instead, we record the installed packages and their versions in requirements.txt. That small file should be committed alongside the project's source code. Another developer can create their own virtual environment and use pip install r requirements.txt to recreate the project's package environment. When we finish working, we can run deactivate. When we return later, we move into the project directory and activate the environment again. The complete workflow is simple. Create, activate, install, record, deactivate, and reactivate whenever you return to the project. I've really enjoyed putting this tutorial together, and I hope virtual environments now feel practical rather than mysterious. If you found the video useful, please give it a like and subscribe to the channel. I know you hear that request all the time, but those small actions genuinely help useful tutorials reach more people. I've included links in the description to several good Python books that explore virtual environments and Python development in greater depth. If you'd like to learn more about managing Python packages, watch my pip tutorial next. It's shorter than this one, but every bit as useful. Thanks for watching, and I'll see you in the next tutorial.